the least common multiple, which we will denote with the capital letters LCM, the least common multiple of two or more polynomials, will be helpful when adding or subtracting rational expressions with denominators that are not the same. The least common multiple of two or more polynomials is the simplest polynomial that is a multiple of the original polynomials. What this means is that the LCM must contain all the different factors in each polynomial, with each factor raised to the greatest power of its occurrence in any one of the polynomials. You can always find a common denominator of two or more rational expressions by multiplying their denominators. However, if you use the least common denominator, which is the least common multiple of the denominators, not just the multiple of the denominators, you may have less simplifying to do. After the rational expressions have been written with a common denominator, you can simply add or subtract using the rules given at the beginning of this section. Let's look at an example to understand what this means. For number 42, we are being told to find the LCD, the least common denominator of the two fractions, and then rewrite each fraction using the least common denominator. Okay, how are we going to do this? Let's look at this. We have two rational expressions for number 42. First one, y minus 4 is over 2y plus 14. Second one, 3y is over 10y cubed. Now, how do we find the LCD? That has that word denominator in it. Let's only focus on the denominators. We have 2y plus 14, and we have 10y cubed. Let's factor the denominators. Notice over to the right, it says you can always find the LCD in terms of its factors. What does it say there for the LCM definition? It says the LCM, which directly corresponds to the LCD, contains all the different factors in each of the denominators. So for our denominators, we factor 2y plus 14. 2y plus 14 is a binomial. Go ahead and go to the full view. So we have our two denominators written. Now this would be on your scratch paper off to the side. For 2y plus 14, it's a binomial, right? We are summing together two numbers, therefore it's a binomial. Bi meaning two. 10y cubed is a monomial. It is one single number, one expression, 10 multiply y cubed. Here, 2 multiply y is summing 14. Remember that terms are separated by plus and minus signs. There's one plus sign, therefore there's two terms, binomial. There is no plus or minus sign. If there's a minus in the front, it just means it's a negative number. This is one single number, it's a monomial. For the binomial, is there a greatest common factor? 2 is multiplying y, 7 is multiplying 2. 7 times 2 is 14. Thus, we could factor out a 2. What multiplies 2 to give us 2y plus 14? Y plus 7. So what are we seeing here? We see that for our first, and I'll go back to the PowerPoint, for our first rational expression, y minus 4 over 2y plus 14, we could rewrite this. We could express this as y minus 4 over, now instead of writing 2y plus 14, let's write it in terms of its factors, 2 multiply y plus 7. And why are we doing this? As it says here, for the LCM must contain all the different factors in each polynomial. For the LCD, what it means is for each of the factors in our denominators, the LCD will contain each different factor in each of the denominator. Each of the denominators. And here, in this case here, 10y cubed. What is 10y cubed? 10 is multiplying y cubed, so we have all these factors here. 10 is 2 times 5. Y cubed just means we have 3 factors of y. So a factor of 2, a factor of 5, a factor of y, a factor of y, a factor of y. So we have 2 factors that make up our first denominator. We have 5 factors that make up our second denominator. So to find the LCM, or in this case here, the LCD, The LCD is going to contain all of the different factors in each polynomial, or in this case here, in each denominator, with each factor raised to the greatest power of its occurrence in any one of the polynomials. What does that mean? Well, here, this factor of 2, there's only one factor of 2 in this denominator. There's only one factor of 2 in this denominator. Each factor raised to the greatest power of its occurrence. What it means is, because there are two factors of 2, we are not going to place both of those factors over here. We're only going to place one factor of 2 in the LCD. The reason why is because it says to the greatest power of its occurrence in any one of the polynomials. This 2 does not have an exponent. Therefore, it's understood to have an exponent of 1. So which one is the greatest of those two exponents? Well, they're the same. It's 1. So we only place one factor of 2 in the LCD. This has a 5. There's no 5 up here. But we're not looking for greatest common factor. For a greatest common factor, they have to be the same. For the least common denominator, we are collecting all of the factors together. So a factor of 2 must be in the LCD. A factor of 5 must be in the LCD. Here's the factor of y, but how many y's do we have? We have 3 factors of y. Therefore, all 3 factors of y must be in the LCD. It says right there, with each factor raised to the greatest power of its occurrence. This factor of y has a power of 3. Therefore, y cubed is in the LCD. The last factor we have not selected, the y plus 7. The y plus 7 multiplies 2, thus y plus 7 is also a factor. So our LCD, the least common denominator, in other words, the expression, whatever it is, the algebraic expression that is the smallest such number that can be divided by both denominators. It's a little bit more difficult to visualize this when you see it as an expression, but just see here that how do numbers divide into one another? Well, they have to have the same factors. The reason why that 8 can divide into 56 is because 56 has a factor of 8. 56 is 7 times 8. And those factors cancel out nicely. 7 times 8 divided by 8 is 7. Thus, 56 divided by 8 is 7. What else do we have? 64 divided by 16 is 4, because 64 can be rewritten as 16 times 4. And thus, we cancel the factors. Same thing here. This LCD here can be divided by 2y plus 14, because 2y plus 14 is the product of 2 and y plus 7. And because those two factors live within the LCD, that means that this number can actually divide into the LCD. Same thing for 10y cubed, which is expressed as 2 times 5 times y cubed. Note that all of those factors live within the LCD, thus 10y cubed can actually divide into the LCD. And just to simplify some things out here, of course, we could rewrite this, and we will. 2 times 5, we know what that is. It is 10, so we can express this LCD as the LCD is the product of the factors, so 10 multiply y cubed multiply y plus 7. That product of those factors is the expression that is the LCD. It is the expression that is the smallest such number that can be divided by both of our denominators. But what did the PowerPoint say? It said take it a step further. Rewrite each fraction using the LCD. So how would we do that? Remember, our objective here is to be able to add and subtract rational expressions with unlike denominators. In other words, for these two rational expressions, their denominators are not the same. A factor of 2, a factor of y plus 7. A factor of 2, a factor of 5, and 3 factors of y. In other words, if these denominators were the same, this 2 is already over here. So if this factor of y plus 7 could somehow be over here, and likewise, if this factor of 5 and these 3 factors of y could be over here in this denominator, we would have the exact same denominator. And that's exactly what we're going to do. By exposing each denominator, or excuse me, each factor in our denominator, we now can build the terms on each numerator and denominator, thus making our denominators like and allowing us to combine. Remember, like just for the fraction 2/3, 2/3 is simplified. But it's always important to know that we can build up the fraction 2/3 to 4/6, 6/9, right? What else? 14/21. Any number that is a ratio of 2/3, whether it's simplified or not, represents 2/3. And it's the same thing here for these rational expressions that are simplifiable. This one we could cancel out a factor of y, but for a fraction such as y minus 4 over 2y plus 14, it's fully simplified. We cannot cancel any common factors. This is a simplified rational expression. Sometimes it's important to be able to build up this rational expression into higher terms to allow us to add and subtract rational expressions with unlike denominators. Denominators are not the same. This denominator needs this factor of 5, and it needs these 3 factors of y. So let's place them over there. The 5 and y cubed, we need the factor of 5 down here. We need the 3 factors of y cubed. If we're going to place those factors in the denominator, we must also place them in our numerator. We have to build both terms of the numerator and denominator. This y minus 4 is also going to get multiplied by a 5, and it'll get multiplied by the y cubed as well. For our previous one, I had to erase. Let's go back and see what that one was. The 3y over the 10y cubed. Well, look at what our LCD is. This will help us determine what factors need to be placed down here. This 10y cubed, where 10 is 2 times 5. Okay, so this factor of 2 that was over here is already over here. The only factor that was in this denominator that's not over here is the y plus 7. So we're going to place the factor of y plus 7 in the denominator. But we must also place that factor of y plus 7 in the numerator. And this is interesting because, again, at any time, remember, y plus 7 divided by y plus 7, we can always cancel those 2 factors out and get back with where we started. But we don't want to reduce or simplify. We're trying to do the opposite of that to allow ourselves to be able to perform the operations of addition and subtraction. By multiplying the same factor in both the numerator and denominator, remember that idea that if you multiply and divide by a 3, you're not really changing anything. If you have $5 multiplied by 3 is 15, divide by 3, you're back down to $5. Performing the operation of multiplication and division, because this is under the divisor, therefore we're dividing by the 10y cubed, we're dividing by the y plus 7, we're also multiplying by a y plus 7. Those operations can be canceled at any time, but we want this operation here. Likewise, in this numerator, this denominator, are these the same now? They don't look the same, right? Well, of course, by rearranging this factor of 2 and this factor of 5, we can rewrite that as 2 times 5, which is 10. By rearranging this factor of y cubed to the right of the 10, and now we have this factor of y plus 7. 10y cubed times y plus 7, 10y cubed times y plus 7. We now have 2 rational expressions, and of course, even on this side here, we'd want to do a little bit of work with it, right? The 5 times y cubed, maybe move that out front of your binomial. And of course, you look here and say, well, the y cubes are top and bottom. We need to cancel those. Remember, that's not the objective here. The objective was to rewrite these fractions in such a way that they have common denominators. By finding the LCD and understanding which factors need to be moved to one expression and to the other, we now see by introducing those factors top and bottom, the 5y cubed to the numerator and denominator of our first expression, by introducing that factor of y plus 7 to the numerator and denominator of our second expression, we don't change the overall value of our expression, but we manipulate it in such a way that it looks different, but it now would allow us to combine these 2 expressions. Because what do we know about 2 fractions that have the same denominator? We can add and subtract those and combine them into one single rational expression. For number 45, we have the denominators 2v squared plus 2v, and we have the denominator 3v squared. by factoring our denominators. 2v squared plus 2v. We see again this is a binomial. There are v's in each term, and there's a 2 in each term. So we can factor out a 2, factor out a v. What do we leave behind here? A 2v out of v squared, or 2v squared, we leave behind one factor of v. If 2v gets moved out, we leave behind the factor of 1. So we have the factor of 2, v, and v plus 1. That makes up our denominator of 2v squared plus 2v. And then for 3v squared, where 3 is a prime number, and v squared represents 2 factors of v. So 3 times v times v. We see that the greatest common factor is v, but what is the least common multiple and thus the least common denominator? Let's go to the full view here and collect the factors. Least common denominator here, we're going to look at all the factors that consist of the denominators. We have a factor of 2, a factor of v, and a factor of v plus 1. So all of those factors are going to go into the LCD. Also, for this denominator, the factor of 3 isn't already displayed, so it needs to be added. This factor of v is already displayed. However, what is this here? This is v squared. And up here, although this right here says v squared, right, we would think that that's where this is coming from. But when we factored this denominator here, it contains only one factor of v that is common. So there's only one factor of v in this denominator. For this one here, however, there are 2 factors of v in 3v squared. Thus, our LCD is going to contain the factor of v with the greatest, largest exponent or largest power in any one of those two. And since it's v squared as opposed to the v, this LCD here will be v squared. So notice here that this factor of 3 is here. This factor of v squared is here. Okay, up here in this denominator, this factor of 2 is displayed. This factor of v is displayed within the v squared, and this factor of v plus 1 is displayed. The LCD is just the collection of the factors that make up our denominators. So 2v squared times v plus 1 times 3. Rearranging these factors, 2 times 3 to give us the 6. Just to simplify that out a little bit, our LCD here is the product of 6, v squared, and v plus 1. So how's this going to help us here for building up our rational expressions? Well, for number 45, again, we have there 6v squared times v plus 1. For the first expression here, v over, and we said 2v squared plus 2v is 2v multiply v plus 1. For 4 over 3v squared, this v plus 1 factor, and I'll go to the full view. This v plus 1 factor, according to our LCD, that's what we want our new denominator to look like. That's the reason why we find the LCD, is because our LCD now is going to tell us what our denominators should look like. So to rewrite the 2v multiply v plus 1 as 6v squared multiply v plus 1, what factors must we introduce? To go from 2 to 6, we had to multiply by a 3. We're going to multiply by a 3 in the denominator. We have to do that to the numerator as well. Anything else? This is now just 6v times v plus 1. We need another factor of v in here. But if we put a v down here, we've got to put a v up here as well. So our new expression here, with a denominator of 6v squared times v plus 1, our numerator will now become v times 3 times v, which rewrites as 3v squared over, and I'll simplify the denominator, 2 times 3, you give us the 6, v times v to give us the v squared, and this additional factor of v plus 1. So note that this rational expression here represents the same exact rational expression of v over 2v squared plus 2v, our original expression. For the second expression, 4 over 3v squared, just to confirm that, 4 over 3v squared, we now want to make our denominator here look like this denominator. So by doing so, to make this 3 is 6, we multiply by a 2. We do so in the numerator and denominator. So now this is 6v squared, but we now introduce the factor of v plus 1. But we do so in both the numerator and denominator. So our numerator now, 4 multiplied 2, multiply v plus 1. Well, 4 times 2 is 8. And this 8 here is going to multiply v plus 1. For our denominator, 3 multiplied 2 to give us the 6, the v squared, and the factor of v plus 1. So note here now that our two rational expressions that previously were unlike denominators now have like denominators, and this would allow us now to combine these two expressions using addition or subtraction. Only other thing we could do here if we want to, and we would want to if we were trying to perform simplification of addition or subtraction, in our numerator now, we have the product of 8 and v plus 1. Go ahead and distribute that. 8 multiply v to get 8v. 8 multiply 1 to get a positive 8. The denominator, you can leave it simply as the product of the factors. We know this is the LCD. These are now common denominators. We leave them as factored because in the event that we combine rational expressions that now have a common LCD as our denominator, when we combine the numerators using addition or subtraction, by combining like terms, we then look at the single rational expression and we note, is there any way that we now can factor this new numerator in such a way that it shares a common factor with the denominator, thus allowing us to simplify our rational expression much further. Remember, we're never done simplifying until we have only one single rational expression where the numerator and denominator do not share any common factors. With number 47, we have two rational expressions where the denominators of our rational expressions are quadratic, x squared minus 25, as well as x squared minus 10x plus 25. Notice the similarities and differences. Each of these are quadratic expressions. However, the first quadratic expression is a binomial, and the third is a trinomial. The second expression is a trinomial. The first is a difference of two squares, squaring an x to get x squared, squaring a 5 to get 25, the difference of two squares perfectly factors into the binomial product of conjugates. The product of x plus 5 and x minus 5. According to FOIL, inner and outer product 5x and negative 5x will cancel, leaving you with the product of first and last terms, x times x, positive 5 times negative 5, which is in fact x squared minus 25. What about our our trinomial there? Trinomial is also a special trinomial in that it is a square of a binomial difference. How do we know that? Well, again, 25 is in fact a perfect square, so is the x squared. 5 squared is 25. Well, notice that number 5, when you double 5, you get 10. When you double negative 5, you get negative 10. When you square negative 5, you get positive 25. Why is this important? Square of a binomial sum says we have two of the same factor, and that is x minus 5. In other words, two numbers that multiply to give you positive 25 that will combine to give you negative 10, that's negative 5 and negative 5. We see again that negative 5 multiply negative 5 is positive 25. Inner product negative 5x, outer product negative 5x combines to give us negative 10x. And as always, first term product here, x times x to give us the x squared. We see here that the common factor between the two is the x minus 5 factor. Each of these contain the x minus 5 factor. Therefore, the greatest common factor, those that are shared between the two, is x minus 5. The least common multiple, thus the least common denominator, is going to be the collection of these factors. In other words, here going to the full view, looking at the factors that make up our denominators, the LCD in this case would be, well, up here we have one factor of x plus 5, so it must be in the LCD. Up here we have one factor of x minus 5, so it must be in the LCD. Now what about down here as we look at these? There are two factors of x minus 5. So two factors of x minus 5 must be displayed in the LCD. And that's it. The product of x plus 5, x minus 5, and x minus 5 give us our LCD. In other words, this is the smallest such expression that can be divided by both the x squared minus 10x plus 25, i.e. the product of x minus 5 and x minus 5, as well as the product of x plus 5 and x minus 5. It's neat. It's how do you know they divide? Well, take this and write it over this one. Cancel the common factors, and that tells you what the quotient is. This LCD divided by x squared minus 25, well, cancel the x plus 5 and x minus 5 factors, and you're left with x minus 5. That is the quotient. Well, what is the quotient of LCD here and the trinomial? We'll cancel the x minus 5 factors, and you're left with the quotient of x plus 5. We have our LCD. It's the product of x plus 5 and the two factors of x minus 5. So how do we use this LCD to build up the terms in our rational expressions? Well, again, for the denominators, let's go ahead and consider them as the product of the factors. So x squared minus 25, I'm going to write that as the product of the binomial conjugates. So x minus 8 over the quotient of, or excuse me, over the product of x plus 5 and x minus 5. Well, this almost looks like our LCD. I'm going to go ahead and go to the full view. LCD here contains three factors. Our denominator is the two factors of x plus 5 and x minus 5. We need an additional factor of x minus 5. So in other words, I need to introduce an additional factor of x minus 5 in both the numerator and denominator. So the x minus 8, I will multiply by a factor of x minus 5, but I also will now multiply the denominator by an x minus 5 factor. Notice at any time I can cancel those two back out and be right back with what I started. But I'm not trying to do that. I'm trying to go the opposite way. I'm trying to build this up. What about the second expression with numerator 9x and denominator that can be rewritten as the product of x minus 5 and x minus 5? Go to the full view. How can we rewrite this denominator as the LCD? We need to introduce the factor of x plus 5. Multiplying an x plus 5 to the bottom and the top. Again, as always, because these are factors, x plus 5, these factors can be reduced at any time and take us back to where we started. But what have we done? We have now expressed these two rational expressions in such a way that they have a common denominator. Thus, this would allow us to combine them using addition or subtraction. Before we do so, we would want to, first, let's clean up the denominators by rewriting them a little bit more properly. Just kind of simplifies that look a little bit by using our definition of exponents to not have to write all that out every time. What happens to the numerators? We'll do the easy one over here. This 9x is multiplying x plus 5, so to distribute the 9x, 9x, 9 multiply x is 9x squared. The 9 times x times 5, well, 9 times 5 is 45. And 45 times x gives us the plus 45x. So that's what that second rational expression would look like there. What about the first one? Well, in the numerator, we have the product of two binomials. So we distribute x times x to give us x squared. Our inner product is negative 8x. Our outer product is negative 5x. Negative 8, negative 5 combine to give us negative 13x. Negative 8 times negative 5 is positive 40. Yeah, multiplication is just addition, right? 8, 16, 24, 32, 40. 5, 10, 15, 20, 25, 30, 35, 40. From trinomial divided by the product of our x plus 5 and 2x minus 5 factors. Notice here how nice it is to see this, because previously it's very hard to get that visual of how these two fractions could be combined. Now that their denominators are the same, notice that their numerators are also quadratic. It's very easy to add two quadratic expressions or subtract them, because in order to add or subtract two quadratic expressions, just like any polynomial, you simply just combine like terms. So if we wanted to add together these two fractions, now that their denominators are exactly the same, we can just combine their numerators using addition or subtraction. For addition, the x squared plus 9x squared is 10x squared. The negative 13x plus 45x would be the 32x. And then the plus 40 we would leave the same. If we were subtracting this, it would be x squared minus 9x squared, which is negative 8x squared. It would be minus 13x. Subtract 45x, you're getting even smaller. You start at negative 13, you subtract 45, you're at negative 58x. And lastly here, this positive 40 has nothing to subtract. It stays positive 40. So once we find our LCD, we use those factors that make up the LCD to build up the terms for our rational expressions, thus creating common denominators. Once we have our common denominators, and once we have our numerators distributed and simplified out, we then can combine the terms by using our rules of polynomial addition and subtraction. Find those that are in fact like terms.